Hello, everyone, and welcome to today's live broadcast, Protein Sample Evaluation using the NanoDrop One UV-Vis Spectrophotometer. It is presented by Voula Kodoyianni, PhD, the Product Marketing Manager for NanoDrop Instruments at Thermo Scientific. I am Judy O'Rourke of LabRoots, and I will be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Thermo Scientific. For more information about our sponsor, visit www.thermofisher.com. Before we begin, I'd like to remind everyone this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, please use the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Dr. Kodoyianni. I will now turn the presentation over to her.
Hello, everyone. Thank you for joining us. In today's presentation, we will cover protein concentration measurements, in particular measurements using the NanoDrop instruments. We will go over some of the basics of direct measurements with A280 and A205. We will talk about colorimetric assays. Did you know that we can do colorimetric assays on NanoDrop One? Yes, we can, and we can even measure labeled proteins. I will end with best practices and tips. Most protein workflows require accurate determination of protein concentration. There are multiple techniques for that purpose, both direct and indirect methods. Each of these techniques has advantages, limitations, and specific requirements. The most commonly used method is absorbance at 280 nanometers. It is popular because it's very simple to use, very straightforward to perform. And another method is absorbance at 205 nanometers. This method is based on absorbance of the peptide bond, and all proteins have peptide backbones, so it applies to even proteins that do not have tryptophans or tyrosines. There are also indirect methods for evaluating protein concentration. For those methods, you have a dye that interacts with a protein to produce a dye-protein complex, and that complex absorbs light for the colorimetric assays or fluorescence for the fluorescence assays. And then by measuring the complex, you can calculate the concentration of the protein. Let's talk about making protein sample evaluation with the NanoDrop spectrophotometers. Many of you probably are already using NanoDrop instruments, but some of you may not. There are just two key things that I want to talk about NanoDrop instruments. One, of course, that most people know is the fact that you can measure without using a cuvette. NanoDrop instruments have unique pedestal technology that lets you pipette your sample. You can pipette 2 microliters of protein directly on the measurement surface, which I will refer to as the pedestal. And then when you close the arm, the sample is drawn into a liquid column using surface tension. And optical fibers transmit the light from the source, the light source, which is a xenon lamp, through the column to the detector, and that's how you see a spectrum. After the measurement, it's very easy to clean up. The sample is simply wiped off, and that there is no carryover. An equally important aspect of NanoDrop technology, and one that not everybody realizes, is the fact that by not using cuvettes, we can control the path length. The path length in a cuvette is fixed. It's usually 10 millimeters. But with NanoDrop instruments, we use a patented auto-range path length technology. And in fact, every sample is measured at multiple path lengths. For the NanoDrop One, it's 5 path lengths, the shortest of which is 30 microns. 30 microns is about half the thickness of a piece of paper. So what does it mean to be able to measure at very short path lengths? It means that you can measure very concentrated samples. Since the concentration is measured by using the Beer-Lambert equation that you see here, the path length is part of this equation, and when the path length is shorter, we can measure very, very concentrated samples. And what that means is that you, the user, never have to worry whether your instrument or your sample is within the dynamic range of the instrument, because essentially you always are within the dynamic range of the instrument. The NanoDrop One and One C is our latest NanoDrop product. These instruments were launched in late 2015. They have some very special features in comparison to other NanoDrop products. The most important one, I think, is that you don't need a PC to run these instruments anymore. There is a touch screen interface, and you can control the instrument from the touch screen. Another very, very important feature for the NanoDrop One is the Acclaro software. Acclaro software identifies contaminants in samples, in both nucleic acid and protein samples, and gives the corrected concentration. And I'll talk about that a little more later on in my talk. This is a very modern instrument with enhanced connectivity. You can connect to a printer via Wi-Fi. You can connect your computer via Wi-Fi and send your data to your computer so that you can analyze it later on at your desk. You can save your data to the Thermo Fisher Cloud, and every NanoDrop customer can obtain for free 10 gigs of memory on the Thermo Fisher Cloud. And the dynamic range for this instrument is huge. You can measure up to 400 or more mg per mil of IgG. We have the NanoDrop One that has the pedestal only, and another model is the NanoDrop One C that gives you the pedestal microvolume capability as well as a cuvette capability. The NanoDrop One has multiple hard-coded applications for protein quantification. All the applications live under the protein tab. Here you can see the protein's home screen. And the other 3 images on this slide show you what the data looks like when you measure proteins with A280. These are measurement screens from proteins and labels and from the BCA colorimetric assay. You can, of course, measure proteins on our other NanoDrop instruments. The NanoDrop Lite is the most basic and smallest model we have. You can fit it essentially in the palm of your hand. And This instrument does not provide spectral data. It is based on two LED lamps, one at 260 and one at 280. So you can collect quick A280 measurements for pure protein samples. The other two instruments, the NanoDrop 2000 and the 8000, both require PC to operate, and they're both full spectral instruments and have a xenon lamp as the light source. The NanoDrop 8000 is our higher throughput instrument. You can measure up to 8 samples at a time. So you can actually do a 96 well plate by loading 8 samples on the 8 pedestals at a time. People that are very good at this can actually do a 96 well plate in 5 to 6 minutes. The output from the NanoDrop 8000 includes spectra for every sample, for all 8 samples at a time. So why use NanoDrop UV-Vis spectrophotometers? Of course, the microvolume capability is very important. You don't waste precious sample. You can measure just from, for proteins, is 2 microliters of sample. It's very fast and easy to measure. You never need to make dilutions because you're always within the dynamic range of the instrument. Dilutions not only take time, but they also introduce errors, so that is important. These instruments are designed for life scientists, so you have other applications that may be of importance to you. You have an 8 to 60 application, for example, as well as just a very basic UV-Vis application. For the NanoDrop One, the Acclaro sample intelligence technology can give you a lot of information about the quality of your sample, and it's excellent value for the customer because you don't need to buy disposables or cuvettes. Okay, now let's talk about protein quantification using absorbance at 280. A little bit about the basics of UV absorbance. UV absorbance is an analytical method that relies on measuring a light beam as it exits a solution. You collect a spectrum that tells you how much that solution actually absorbed, and these spectra give us both qualitative and quantitative data. Qualitative data because the spectral fingerprint tells us what molecules are present in the sample. And quantitative data because at a given wavelength, the absorbance is proportional to the concentration of the absorbing molecule in that sample. And then we can use the Beer-Lambert equation to calculate the concentration from the absorbance at that wavelength. Proteins absorb at 280 because they have amino acids that have aromatic side chains, and they absorb around 280. Tryptophan is the most important amino acid for A280 because it has the highest extinction coefficient. In other words, it absorbs the strongest of all amino acids. But tyrosine also contributes. The cysteine disulfide bonds contribute, and phenylalanine contributes to a smaller degree. So a typical, on the right, bottom right here, you can see a typical protein spectrum. It will show you a peak at 280 and also a strong absorbance from the peptide backbone, a little lower at around 200. So from A280 measurements, absorbance A280, we can calculate the concentration using the Beer-Lambert equation, as I said. So the Beer-Lambert equation says that A280 equals concentration times a specific factor that's protein specific, that's called absorption or extinction coefficient, times the path length, that the distance that the beam travels through the sample. This epsilon value is a very, very important number. Epsilon is the wavelength-dependent absorption coefficient. It can be molar or it can be mass, and we'll talk more about that. It is based on the amino acid sequence, and it is different for every protein. Unlike nucleic acid samples, where if you have double-stranded DNA, the epsilon is a factor that's the same for all double-stranded DNA. That's not the case for proteins. For proteins, every protein has its own distinct epsilon value. A couple of other things that will be good to keep in mind when we use direct A280 measurements. Calculation assumes that the protein is pure. In other words, it assumes that all the absorbance at 280 comes from this protein. In reality, there are sometimes other contaminants in the sample, and everything in the sample that absorbs at 280 nanometers will contribute to that A280. What can that be? Nucleic acids absorb at 260, which is nearby. Some buffers and detergents also absorb nearby. Something else to keep in mind is that the secondary and tertiary structure of the protein can affect the absorbance. So sometimes spectra from the same protein can look different when the protein is dissolved in different buffers. Let's talk a little bit about epsilon, extinction coefficients. They come in two flavors. They come as the mass extinction coefficient, which is essentially the absorbance of a 10 mg per ml solution. These numbers can be determined empirically, but coefficient values for many, many proteins have been compiled and are available in the literature. So you usually just look them up. In addition to the mass coefficient, we can have a molar extinction coefficient or absorptivity coefficient. And that is the molarity of the protein solution that gives you a 1 absorbance unit. These two flavors of extinction coefficients are related to each other, so if you know the molecular weight, you can convert one to the other. NanoDrop makes it very easy for you to select the correct extinction coefficient. And when you are doing a measurement, you will be asked to select a sample type. So what is a sample type? The sample type tells the instrument what extinction coefficient to use to calculate protein concentration from A to 80. Remember Beer's law? Beer's law knows the L, knows the path length of the instrument, knows the absorbance, but to calculate the concentration, it needs to know which epsilon value to use. And that is what you do when you select the sample type. The proteins on the drop-down box give you a range of extinction coefficients. Of course, if your sample is IgG, it's very easy. You select IgG, which would be a usable mass coefficient for most mammalian IgGs. But also, if you know that your protein has an epsilon value of near 7, and I think it would be smart to pick BSA as your sample type, because that means that the calculation will be using an epsilon of 6.67. So these proteins give you a range of extinction coefficients that you can use. Now, if you know your molar coefficient, you can enter it under other protein E, epsilon, and molecular weight, but you have to enter the molecular weight in this case so that the instrument can calculate the mass coefficient for you. And if you know the mass coefficient, you can just enter it under other protein, epsilon 1%. Sample type ensures that the correct factor is used in the calculation of the protein concentration. So what I have here is an example that illustrates the importance of using the correct epsilon value. So we have a sample that has an absorbance at 280 of 2. The first calculation uses BSA as the sample type and uses a mass coefficient of 6.7. The concentration result would be 3. The second one uses IgG, so the concentration will be 1.5, half as much, because the mass coefficient is 13.7 compared to BSA. So you can see this way how epsilon can affect your concentration result. Epsilon values range from 4 to 24. So if you have a sample that's a mixture of proteins, or it's a pure protein that you don't really know the extinction coefficient, or you only need an average value or an estimate of the protein concentration, we have an option, the one absorbance equals 1 mg per mil, that you can use. And this one is based on an epsilon mass extinction coefficient of 10. This table gives you more detailed information about the sample type options that NanoDrop gives you. I've included this for your reference in case you want to look at the details at a later time. On the NanoDrop One, we have added a new feature that we believe will make protein scientists' life a lot easier. And that new feature is the protein editor. What the protein editor does, it allows you to customize your sample type drop-down list. So the way it works is from the home page, you can tap on the settings icon, and then you select the protein editor. The protein editor then has a plus sign there. If you tap on the plus sign, you will be prompted to add information about your protein, such as extinction coefficients, molecular weight, and so on. And a name. You can call it my favorite protein or my fibronectin or whatever. And then when you save that, that entry, then your favorite protein will become part of that drop-down box, and you can select it every time you make a measurement. This should save a lot of time and also reduce error due to typos and so on. Before you do any measurement, you have to blank the instrument. And you usually blank with the buffer that your protein is dissolved in. With the NanoDrop One, when you blank, you do not see a spectrum appearing on the screen. But the blank spectrum is collected, and it is saved in the instrument memory. And then it is subtracted from each measurement, each subsequent measurement, until you do another blank. This way, the buffer contribution to absorbance is removed, and the sample spectrum that we see, it really is all due to the absorbance of the protein in the sample. It is important that you blank with a buffer that is the same buffer that you have used to make the protein solution from the same bottle, if at all possible. The baseline correction is something completely different. When you set up an experiment on a NanoDrop instrument, you see that you have a baseline correction set at 340 nanometers, and you can deselect that if you don't want it. So the baseline correction is used to correct for any light scattering that's caused by the sample itself. Samples sometimes have microbubbles or particulates that can create scattering, light scattering in the sample, and that can affect the absorbance. So what essentially it does, it normalizes each spectrum to a specific point in the spectrum by subtracting the absorbance at that wavelength. And that wavelength for proteins is 340 nanometers, where absorbance is minimal for protein samples. Now, if you have a sample that for some reason absorbs strongly at 340, you should turn the baseline correction off. Otherwise, you will see an underestimate of the absorbance. Talk about buffers. When measuring concentration using A280, one should consider the protein sample buffer. The buffers on the first row of here that are, you see spectra of PBS, heaps, and chats. These are buffers that you would consider good. We took measurements of these buffers, blanking first with water, and you can see that these buffers are pretty flat around 280, even though they do have some absorbance in the low UV. RIPA buffer does absorb quite strongly in the low UV, especially around 280. So RIPA is not recommended as a buffer for A280 quantification. Now, when you are in doubt whether your buffer is good to use in measuring A280, you can evaluate your buffer yourself by blanking with water and then measuring, looking at the spectrum of the buffer and seeing if you have absorbance around the area, the wavelength of interest. What happens if you do use RIPA buffer? I have some examples here of measuring a BSA solution. And the first one, in figure 1 on the left, we have a BSA solution in PBS, and the blank was PBS as well. You can see a typical correct absorbance spectrum that has a trough around 240 to 260 and a peak around 280. In figure 2, the red arrow shows you a spectrum of BSA in RIPA buffer with blanking in water. This particular solution, the actual true concentration is 15 mg per mil, but the reported concentration is going to be 33 mg per mil, because there is a lot of contribution from RIPA at this wavelength. In fact, this green arrow shows you a spectrum that's just RIPA only, and you can see how much absorbance we have. If you blank with RIPA as well in order to measure a sample that's in RIPA buffer, then you get a spectrum like that in figure 3, which shows you that you basically wipe out all absorbance. So it's best to not use RIPA buffer for A280. Making measurements, A280 measurements on the NanoDrop One is very, very simple. You select the protein A280 application from the home screen. You blank the instrument with a buffer. You will see, you select your protein type, your sample type, and then you close the arm and you will see your measurement here on the A280 measurement screen. The data that you will see is concentration, the absorbance at 280, and then you will see another number, you will see another number, which is the a ratio, A to 60 over A to 80. This is a purity ratio, a protein purity ratio. For those of you that work with nucleic acids, the term purity ratio should be very familiar. To 60 over 280, to 60 over 230 are ratios that give you information about nucleic acid purity. In a similar way, the 260 over 280 can give you information about purity of your protein sample. In fact, this ratio is very sensitive to nucleic acid contamination. If you have nucleic acid, 5% of nucleic acid almost doubles your purity ratio. But for the NanoDrop One, in addition to this purity ratio, the Acclaro sample intelligence technology will give you a lot of information about your sample. And this is how Acclaro works. On the left here, we have a measurement screen. We have a protein sample that has been flagged with a contaminant alert. That's that yellow triangle there. If you tap on the yellow triangle, you will see the contaminant analysis screen on the right. So what this screen tells you, this has a lot of information. It tells you that although the original concentration of the sample was 5 mg per ml, Acclaro has detected that there is a lot of nucleic acid in the sample that contributes 2.59 mg per ml, and that has to be subtracted to give you the true concentration of the sample, the corrected concentration, which in this case is 1 mg per ml. So Acclaro can detect nucleic acid in proteins and give you corrected concentration. For those of you that may be working with nucleic acids as well, Acclaro is a very, very useful feature because it can detect protein, phenol, and guanidine salts in DNA and RNA samples and give you corrected concentration, saving you a lot of time from troubleshooting headaches. Let's talk a little bit about protein A205. Protein A205 is a new feature on the NanoDrop One. It was used as a custom method on the NanoDrop 2000, but we had a lot of interest in it, so we added it as a preconfigured application on the NanoDrop One. Absorbance at 280, as we just discussed, requires tryptophan and tyrosine residues, but not all proteins have tryptophan and tyrosine residues, especially small peptides often may lack tyrosine and tryptophan. So A205 is based on the absorbance of the peptide bond, and that's present in all proteins because all proteins have a peptide backbone. In fact, A205 is much more sensitive than A280 because on average, the molar absorptivities at 205 are much higher, about 30 times higher than the molar absorptivities at 280. The Achilles heel, though, for A205 measurements is that protein buffers absorb strongly in the low UV, and it's very hard to find a buffer that does not absorb. For customers that want to make measurements at A205, we recommend that they use a low absorbing buffer such as the bridge lysis buffer that absorbs minimally in the low UV. So when you open the A205 application, you are going to be asked to select one of three methods. Method 1 is to be used for peptides that have no tryptophans or tyrosines. And this method uses an extinction coefficient of 31 to do the calculation of the concentration from absorbance at 205. If your protein contains significant amounts of tryptophan and tyrosine residues, you should be using the Scopes method. The Scopes method takes into account the significant absorbance of tryptophan and tyrosine at 205 and uses a ratio in its equation to correct for the side chain absorbance. If you already know the exact extinction coefficient of your protein at 205, and you can find that actually using calculation tools that you can find online, you can use the third method, which is the custom method. You can also run protein colorimetric assays on the NanoDrop instruments. Colorimetric assays are commonly used to measure protein concentrations of impure protein mixtures or cell lysates, and they require a standard curve. It is very easy to measure, to do standard curves on the NanoDrop One pedestal. Here we are looking on the right at setting up such a measurement. You can get to pick your curve type, the replicates you're going to use, and you can enter the concentrations of your standard curve. On the bottom right here, you can see a measurement screen at the end of the BCA assay. The white circles here are the standards, and the red are the samples. And on the upper right here, you see the results. You can see the concentration result as well as the absorbance at 562 nanometers. We have many protocols and application notes on colorimetric assays. I've included some links to them here, but you can find many of them on our website. This table is for you to use as a quick reference. It includes the concentrations, protein concentrations that you can measure using the NanoDrop pedestal, as well as advantages and things to consider for each assay. Proteins and labels application. One uses the proteins and labels application to quantitate labeled proteins. Those of you that use the NanoDrop to measure nucleic acids, this is the protein analog of the microarray application. With the proteins and labels application, you can quantitate both the carrier protein as well as 1 and up to 2 dyes. So, for example, a lot of our customers use it to evaluate label incorporation in their sample. Now, I want to make it clear that NanoDrop instruments do not measure fluorescence. They are spectrophotometers. They are not fluorometers. But a lot of dyes also absorb in the visible. And NanoDrop spectrophotometers use this absorbance to calculate dye concentration on labeled proteins. To make To start such a measurement, you select the sample type like you would for the protein, and that is going to be used for the calculation of your protein concentration. And then you can select dyes and units, and you select dyes from a drop-down list. And the instrument comes with a number of preset dyes, but we have a feature that allows you to customize the dye editor, and I will talk about that in a minute. First, I want to show you here a measurement screen. This is a Cy5 labeled antibody. So you can see that you get 2 peaks, 3 actually, but there is 1 peak at 280 from the antibody and 1 peak at 500, which is from Cy5. And then your result includes a concentration, both of your protein and the dye. So as you can do with the protein editor, you can customize the dye editor as well. So you can access it through the settings menu, again, from the home screen. And you can go in, hit the plus, and you will be prompted to add some information as well as a name for your dye. You can also remove dyes. If there's dyes on the drop-down menu that you know you'll never use, you can deselect them and they will not appear. And then enter your own dyes, the one that you use. And you can get all this information, like a coefficient and wavelength where it absorbs. You can get all those from the dye supplier. Now, it's important that the dye you select must fall between 450 nanometers and 700 nanometers. If you have a dye outside that range, you can still do a measurement, a proteins and labels measurement, but you cannot really do it within this application. You will have to create a custom method to do it, and our tech support team can help you do that. We have custom methods available on our website for measuring a number of molecules such as hemoglobin, glucose, nanoparticles, chlorophyll, the Pierce Rapid Gold BCA, which is a new colorimetric assay. You can use that as, you can find that among the custom methods on our website. So what is a custom method? This is a method that can be uploaded to the onboard control of the NanoDrop One. And then you select it, and then you can use it as any other application to do your experiments. Feel free to contact our NanoDrop technical support team to ask questions about custom methods and to get help creating new custom methods. We do that for customers all the time. I want to talk a little bit about tips and best practices for NanoDrop using NanoDrop instruments. For proteins, it's very important to measure 2 microliters. Again, those of you that may be doing nucleic acid measurements, you can go as low as 1 microliter for nucleic acids, but proteins have surfactants and detergents in them that affect the surface tension, and it's important to use adequate volume to make sure you make a good column for measurement. But remember, concentration calculations are really volume independent. Before you measure, make sure your sample is homogeneous. Vortex it, warm it up a little bit. This is especially important if your sample is very concentrated. Use a fresh aliquot for every measurement. Make sure you don't have little bubbles in your sample. Maybe do a quick spin prior to measuring. Make sure you blank with the appropriate buffer. Make sure your pedestals are clean. Occasionally, the pedestals will need to be reconditioned, especially for when you do a lot of protein measurements. And as I said, proteins have detergents in them. Detergents tend to decondition the pedestals, and you know that your pedestal is unconditioned because the sample does not bead on it. It will look flat. In that case, you just have to get the PR1 kit that we offer, and it's a very simple procedure to recondition your pedestal. Okay, I've come to the last slide here. This is a table that gives some basic information. How do I know what is the best method to quantify my protein sample? I presented 4 different methods. How do we know which one is the best? This table gives you some clues. For example, for direct measurements at A280 and A205, your protein must be pure. If you have a cell lysate, colorimetric or fluorescence assay may be better because the sample does not have to be pure. Think of your buffer and buffer compatibility with assays. Think of the time that it will take you to set up the assay. The indirect assays require time and to do the reaction, as well as to create a standard curve. This table just gives you some things to consider. This is my last slide. Thank you very much for joining me.
Thank you, Dr. Kodoyianni, for that informative presentation. We will now start the live Q&A portion of the webinar. Patrick Brown from the technical support team will join Voula to answer questions. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on your screen and click the Send button. We'll answer as many of your questions as we have time for. So let's get started. Our first question is, I had a crude protein extract and wanted to determine protein concentration accurately for bioassay, but due to colored components within the extract, the Bradford method failed to give an accurate result. What other option is there to determine the concentration?
Thank you for this question. It's a good question. I'm going to let Patrick from our tech support team answer it. Patrick, please.
Thank you. So absorbance spectroscopy really cannot differentiate between molecules absorbing at the same wavelength. For accurate quantitation, the sample really needs to have only one molecule in it absorbing light at that particular wavelength of interest, the quantitation wavelength, or as we call it, the analysis wavelength. For this individual, the first thing I would recommend is to use the UV-Vis application. This will give you make a measurement of your sample in the UV-Vis application, and this will give you an idea of what wavelengths your sample absorbs light at. And then consider looking at some of the other colorimetric assays for which we have hard-coded applications, such as the BCA or the Lowry or the Pierce 660, and see if any of those wavelengths specific for those reagents in your sample have minimal absorbance. And so that would be the best option. Now, in the event that those reagents, the wavelengths at which you quantitate those reagents, there's also absorbance in your sample, you may need to think about purifying your protein out of your extract, or alternatively choosing a different method to extract proteins such that there's not so much absorbance in the visible spectrum.
Thank you. Next one is, my colleagues measured DNA and RNA on their NanoDrop. Can I measure my protein samples without harming their measurements?
Okay, that is a good question, and it's one that we hear quite often. Yes, you can absolutely make protein measurements and DNA and RNA measurements on the same instruments. When you finish your measurement with the proteins, You can simply wipe the pedestal with a lint-free laboratory wipe to prevent carryover. Something that one could do if one is worried that and wants to make very clean the pedestals really well is to use PR1 to recondition the pedestals. We have methods of how to more thoroughly clean the pedestal if you're truly worried, but that will take a while before your pedestal is affected by too many measurements with proteins. So bottom line, yes, you can absolutely measure your proteins on the same instrument.
Thank you. Some of my samples are negative. What does that mean, and how do I fix it?
Yes, that's another very good question. So negative absorbance means that your blank is absorbing more than your actual sample. And I will let Patrick talk about this in more detail.
Sure. So as Voula mentioned earlier in the presentation, when you make that blank measurement, the software is storing the amount of absorbance through that blank in the software. And then when the sample measurement is made, the absorbance of the blank is subtracted from the sample. So when your sample reads with negative absorbance, that tells us the blank solution or the blank measurement had more absorbance than the sample itself. That can be caused because perhaps there was something on the pedestal. The pedestal was dirty prior to making that blank measurement, or perhaps even the blank solution itself, be it water or elution buffer, somehow got contaminated. Anytime we see a negative absorbance, we recommend cleaning the pedestals. Again, you can use that PR1 solution that Voula had mentioned. Obtaining a fresh source of your blank, whether it's water or your elution buffer, blank the instrument again, and repeat the measurement.
Thank you. Our next one is protein measurement using A280 sometimes shows poor repeatability. How do you improve that?
That can be due to a non-homogeneous sample. Remember I talked about the tips and tricks, how it's important to make sure that your sample is homogeneous. Make sure you vortex your sample. Maybe you need to warm it up. So that is the key reason that you may see poor repeatability. Patrick, do you have any more ideas about this question?
I definitely agree with those comments. The other common things are definitely use 2 microliters when making protein measurements, and also it's very important that you wipe the pedestal between every measurement. So you would not want to make multiple measurements of the same 2 microliter sample, for example. You would want to wipe the pedestal, go back to your sample tube, and take a fresh 2 microliter aliquot to make another measurement. And those between 2 microliters and using different aliquots, as well as the comments you made, Voula, I think those are some good places to start.
Yes, very, very good.
Thank you both. What protein controls do you recommend?
Well, there are several BCA protein controls that are Thermo Scientific cells. The best thing to do is contact our tech support team. We have lists of standards that you can use. Actually, it's important that, for example, when you do a colorimetric standard curve, that you have a standard that is similar to your protein that you're trying to measure. So, for example, if you're measuring antibody, it's better to use IgG as a standard because they behave in the same way and they bind protein in the same way. So, Patrick, any more ideas on this question?
No, I think that was perfect.
Okay. Do proteins need to be denatured to be measured on a NanoDrop?
Patrick, why don't you answer that?
Sure. Proteins do not need to be denatured to be accurately measured on NanoDrop instruments. They certainly can be. One thing to consider when measuring your proteins is that native folded proteins do absorb light differently than denatured proteins. They may absorb light, more light or less light for the same concentration. So when you are making your protein measurement, you do want to ensure that the extinction coefficient you've input into the protein A280 application was determined on the same conformation of your protein, whether you're measuring native protein or denatured. You want to make sure the extinction coefficient matches what you're measuring.
Great. It looks like we have time for one more question. So it is it possible when using colorimetric assay on NanoDrop One to load previously acquired or measured standard curve and measure the protein concentration without repeating the standard curve measurement?
Patrick, I'll let you respond to this one, please.
Sure. So unfortunately, at this time, we don't have that capability, but we do know that this is a highly requested feature, and we are working, our software team is aware of this feature, and so perhaps in the future that will be available.
Very good. Well, I would like to, oh, sorry, Dr. Kodoyianni, please finish.
That's okay. So with our next software release, we would be adding some features that are highly requested by our customers.
Wonderful. I would like to once again thank Dr. Kodoyianni for her presentation. I would also like to thank Thermo Fisher Scientific for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through September of 2019. Please share with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Goodbye.